Hello. So, welcome to the next video or the next lecture of this series for Mathematics for ML. And today in this lecture, we'll be seeing the vector space, which we have studied a little bit, I guess, in lecture 1 and 2. So, the concepts from lecture 1 and 2 will also be given here. So, you will see that how this correlates with the first and second lecture. It's not so much, but yeah, it is. So vector space. This is just a mathematical term, so we'll properly go over it. So what is vector space? So as I told you, there are some vectors, a v1 vector, v2 vector, v3 vector. So all of them are closed under the loop in some vector space. So vector space, you can think of it as a box which stores all this vector and which is a closed box. So all the vectors you see which are in that box are called as the vectors of that vector space. So this is you can see vector space V of R over the field R. So R is nothing but the real number and V is nothing but the vectors. So this is a set of vectors over the field R. So for our ML, we'll study only with the real numbers. We don't need other numbers. So that's why we are going off V over the field R. So it is pronounced as V over the vectors over the field R. So it is a set of vectors, and we have two operations, which is the addition, which we saw in the operator part, and the scalar multiplication, which was like a in previous videos, like I told you, it is like a volume kind of thing where you scaled up and scaled down the music. Similarly, you can scale up and scale down the scale your matrix or your vectors. So these are defined, and it defines the six properties which it must satisfy. So in summary, what you can think of vector space. Vector space is just a set of vectors where you can perform the addition and the multiplication operation, scalar multiplication operation, and which will be satisfied these six properties. So let us go by these six properties. So let us see this first property. So it is M1, which is first property, is vector with addition is an abelian group. So what do I mean by abelian group? So when you perform the vector addition in the same set of space, so in the same space, they belong in the abelian group uh, by the virtue that they satisfy some of the properties which are like usually given, like commutative property, then closure property, then there are another associative property. So there are some properties which it must satisfy to be called as in the abelian group. So I'll give you a brief example later also ki what does it mean by abelian group. So what kind of properties it must satisfy. So I'll give you an example of it. Then second is the closure under scalar multiplication. So for this scalar multiplication, there is for all A belonging to R and any two vectors belonging to V, W belonging to V. So A is nothing, but it is a real number. It can be any real number, 1, 2, 3, 5, 10, 15, anything. And VW is just a set of vectors. So it is just this is vector 1, this is vector 2. So these all belong to the vector set of space V. So if you scalarly multiply the addition summation of V plus W by scalar A, then it should be A dot V plus A dot W, meaning it should the scalar value should be translated here and here. So A dot V plus A dot W, and this is a real number, and these two are vectors. So this should okay, wait. I've told you the distributive closure is under basically what we both real number and vector v lie under the same. So this is like the distributive scalar over vector addition properties. Closure under scalar multiplication property for all A belonging to R. A is nothing but a scalar constant value, and V belonging to V, which is vector value. Scalar product should also belong to the vector space V, because let's say if there is a vector 0 comma 1 and you multiply this by 5, then it becomes 5 comma, no, sorry, then it becomes 0, because 0 into 5 is 5, 0, and 5 into 1 is 5. So 0 comma 5. So this also belongs to the same set of real numbers and same set vector, because there's nothing that changed here. Okay, so this is our this is belongs to the same vector space. So this is for this under scalar multiplication. For distributive, it is like there's one scalar and there are two vectors v plus w. If you add v plus w and then scale it with a separately, then the result should also lie in the same vector space. Then there is a distributive vector over scalar addition. So this was vector addition, this is scalar addition. So in this, we multiply by the scalar quantity. Here we add the scalar quantity. So a and b are some real numbers, 5 plus 10 or something, and v is the vector. So a plus b into v equals to a into v plus b into e. So you can distribute this here also and here also. Likewise, you can distribute here also and here also. This is what these two properties are telling you. Then M5 is associativity of scalar multiplication. So suppose you have two scalars A and B that belongs to the real number and there is a vector V. Then you can multiply A and B together and then you multiply it by V, or you can multiply first B and V, which is a scalar and a vector, and then multiply it by a scalar. Answer will be same. Nothing will be different. You can use the same example for all the sets, and I'm sure you will get the same answer. If they are saying two scalars, take 5 and 10. You'll get the same answer. If you want to try, you can try it, or you can post it in the comment section, or if you have any doubt, you can also raise it there. Mm, so there is final law, which is unitary law. Unitary law says that there is at least one element, that is one, which belongs to a real number, that for any vector, which is a subset of the big V, 1 dot V equals to V. So one is what? One is the scalar unit 1. So anything multiplied by that into vector will be the same set of vector. And if this V lies in the big vector space, then it should also lie the same vector space, because there's nothing that changed here really. So this is what are the 6 properties, and they should satisfy for it to be called as the same vector space. Now you will be asking me why we are studying this and why is it important. But trust me, this builds upon the basic principles, and later we will study something which will require it. Not exactly this, but it is good to know of this. So let's move to the next part. So let's say this is the example. So I'll tell you what. So let's say this is V belonging to R square. So I have told you earlier also, I'll tell you again. So it gets fixed into your mind, because this is very important. R square means the dimension is 2. So dimension 2 is this A comma B, C comma D. So these are two vectors. This is V1 and this is V2. This is V2. So they all belong to R square kind of R2 kind of a dimension. So your dimension is 2 and R is a real space of number. So then if you add this, then you get A plus C, B plus D, which also belongs to R square. So this is the closure property that holds in R square. So if there are two vectors which you do the addition of, because the first property was what? First property is, can you remember now? It was V and operator plus. This should be this should be in the abelian group. Abelian's group first verification is this. It should be a closure property should be accepted. Like it should be a closure that holds in that specific dimension, whatever it is. So this is proof. Then there's second commutativity. The commutativity. So yeah, sorry guys, this is just a mix up in pronunciation. A comma B and C comma D. These are two vectors that belongs to the real space. Then if you add this, you get A plus C, B plus D. Same result as this. Nothing is changed. Nothing is changing. So if you do A plus C or B plus D, if you just do it here, crisscross. So then C plus A, and if you do it the same here, then D plus B. So both will be C comma D plus A comma B. So this is same. This is same as this. So as you can say, if both of this is same, like this is finally this, then that means it is commutative. So yeah. Then third, let's go for third. So if A, B, C, D, and E, F, there are three vectors V1, V2, V3. If you add them, if you first add C, D, and E, F, and then add A, B, the result will be same. So if you first add C plus E, D plus S, A, B, then A, then C, E, B, D plus F. So you can see here, A will be added, C will be added, and E will be added in the same space. A, C, E, and then BDF will be added no matter what's the priority here is. You can do B plus D, then F. You can do D plus F, then B. Anything is fine, which is done here also. See, so it is first B, D plus F, and then B plus D plus F. Yeah, so this also holds. So yeah, these are the three sub properties for the abelian group. Then let's see the fourth and fifth property for this. Yeah, okay, so why can't I? Wait. Yeah, so this is the next property. Now, when I say this associative property holds, now let's see this property. So this is the fourth and fifth property. So let be A comma B, which is a single vector in R square. Then if you add 0 to AB, you get the same value. So this is the additive identity of the element of R square subspace. So R square space, vector space. Then this is the fourth identity element, and then there's a fourth, there's a fifth. If A comma B, which is the same space of vector, this is the same vector V, it belongs to R. Then there's also A minus and B minus, like minus A minus B, such that if you add both, you get 0 comma 0. So this is like if you get the negative of this same V, so minus, if this is V, if if this is V and you get minus V, then addition of this two should be 0, which you get here. So this is 0 comma 0. So this is all the abelian properties. Okay, then let the second property was our closure under scalar multiplication, which said that if there is a scalar 1 A and if there's a scalar vector V, then both of the multiplication also lies in same space. So this is K scalar, this is vector V. If you multiply this K A comma B, you get the K A K B, which also lies under the same vector space. That means second property also holds. Uh, Now let's move towards the third one. So what was the third one? Third one was which we mistakenly took as second one earlier. So according to that property, we have if there's a scalar A, scalar K, and then there are two vectors A, B, V1. This is V2. Wait, I'll show you. So this is like uh, this is like this is scalar K. This is V1. This is V2. Then if you multiply K by both of this, like the addition, when you add this two vector V1 plus V2 and then multiply by K, then you get the same answer. So K, A plus C, B plus D. You K put in the A plus C, you put K in the B plus D, you get KA plus KC, you get KB plus KD. Same here, KA, KB, KC, KD. So you get K, A comma B, K, C comma D. So this is like the same thing, like K goes here also, K goes here also. So you can distribute it. So that's the M3, which is distributive scalar over multiplication addition. So if you remember, this was like, this property was like A, V plus W equals to, it was AV plus AW. Yeah, so this was the same property that we saw here. Then this is the fourth M4. Then there are two scalars and there's one vector. If you add these two scalars and then multiply it by the vector, you'll get the same value. Like you'll get the same thing as like if you had first the add the both differently and then the combined it into the single one. So like let's say this is the this is our what is this called? This is called distributivity vector over scalar addition. So you add the scalars here, a k plus m. So this was k plus m, and then you add this. Let's say this is v. So ultimately this becomes what? V dot k and m you can add, or you can just do k into v plus m into v. Both will be same. So there's nothing wrong with this. Okay. I think you'll have trouble recognizing this. So I'll write with uh, black marker here. So this is like the same property. You can go through it. Like it's very easy. You just have to do the stepwise process, or either like this way you can understand that they are literally the same. So these are just the examples what we are saying. Like if they are if we can say it is true, we are just looking into it. So then let's do the next. Now this is the next one. So this is M5 and M6. So M5 is K. Let K belong to Km belong to real number, and AB is our vector. So what was our fifth property? Fifth property was the associativity of scalar multiplication. Associative means if you do the scalar multiplication, that is K into M, and then they multiply it by vector, you can also do first one scalar, one vector, and then another scalar. So you can do Km first with V, or you can do K separately and Vm. So this is what it is like. If you do this, so if we do K M A comma B. So A comma B is basically a vector. So and K M is a scalar, K is also scalar. So you first multiply by this, then you multiply by this. Or you can multiply first Km first and then A, and here Km first and then B. So it can also be Km AB. So this is the same thing, this and this. So this is the associative law for the scalar multiplication. Then sixth is unitary law. So if you multiply 1 by AB, 1A, 1B, it is AB. So see, this all M1 to M26 are satisfies. Therefore, we can say that R square of the over the field R and plus n scalar multiplication operation is a vector space. So you can thus you prove that this belongs to the vector space. So we did the property for this. It's very long, it's very cumbersome, but like it shows that it is true. You may also need to do it over some examples, but we'll see about that. This is very cumbersome, I know, but it is like important for the next aspects. So there's some other examples. So V equals to R of the dimension n forms a vector space over R. Then V equals to P form a vector space over R. P can be any polynomial in variable x, and coefficient you can take from any real number. Then V equals to Pn and forms a vector space over N. Pn is a set of all polynomials with degree n in variable x and coefficient are from R. But there is a special case here where it won't work. I'll tell that to you in a brief. So this is like some of the other examples. Then there is a these examples were not forming vector space over R. So you can't form. So this is set of all polynomials of degree n does not form a vector space over R. So why is it? Why do we say okay? I guess something happened. Wait. I think yeah something. Yeah. So we are back. We are back. Yeah. So why is it? Why are we saying this? Why is it so? So do you think there's any truth to this, or like are we really yeah, so why do you think we are saying this? So let's take an example. Vector set of all polynomials of degree n, and here we are saying does not form We are saying it does not form vector space over R. Reason, because vector addition is not closed. So if you have some another if you add it with something and the commutative property or associative property does not hold, then you will be in a mess, because that won't be under the same vector space. So that's why we are saying this. So we'll take it with an example. It's a simple example. It's written over here only. So see, if there's x1, x2, this is x1, y1, this is vector 1, this is x2, y2, this is vector 2. If let's say like this is not generally true, but let's say the addition of this two goes as this x1 plus x2 and y1 plus 2y2. Okay, so this and this and y1, and you add twice of y2. Okay, this is not true by standard means, I'm telling you again. But let's say this happens by some virtue of the law, that there is a law that say if you add these two vectors, there will be x1 plus x2. First are added simply, and second is added y1 and second of 2y2. If you reverse it, then tell me what is it. If you reverse the if you do the commutative thing, then what do you get? So if I just reverse it, I'll get x2, sorry, just x2 comma y2, and you will get x1 comma y. And if you add this together, what you will get? You will get x2 plus x1, which is cool. Okay, which is cool, because you are getting the same value as x1 plus x2, because both are same. They're just changed by the order. But in the next part, you will get y2 plus 2y1. Now tell me, do we want this? Do we want this second term, y2 plus 2y1? We don't want it, right? We don't want it. Why we don't want it? Because it does not tells us anything about the because it does not hold the commutative property, and that's why we can't have that. So that's why the R square of R with addition is not an abelian group, because of this nature of it. So this is how you can also prove that if something is a lies in that abelian group or something not. You will be given the you'll because in ML you'll know the features and all, and you'll have to do the dimension detection, which we'll talk later, of course. Right now, it won't be of any virtue for you. So, okay, like here, then let's start with the subspaces of R. Just understand this part first, that we can't have anything as an abelian. We have to first prove if it is an abelian, then we can go over it. And some kind of examples do lie along the subspace, but some do lie along the vector space, but some of it does not. So this vector of all polynomial of degree n does not. But if R raised to power n or p or n, this kind of things do lie under the same vector space. So that is important. Then let's talk about the subspaces of R raised to Rn. So what is the subspace specifically? What am I telling you if I'm saying subspace? So subspace is nothing, just if R of n is an vector space, then there is a subset of vectors that belong to the real numbers of n dimension, which is said to be a subspace of V equals to R of n of the field R if 0 belongs to that S is that subset. If 0 belongs to that subset, S is closed under vector addition, that is x comma y belongs to S implies x plus y also belongs to S. So this should also be done. And S is closed under scalar multiplication. So we have V plus and dot. So plus comes under second law, dot comes under third law, which is x should belongs to S and alpha belongs to R. Implies x is any vector. Okay, so it implies that x vector multiplied by alpha should also come under the S subset. So what do we say? Let's brief it up. We know there is one vector. Vector is a set of all vectors that are closed under loop. It can be v1, v2, v3, v4, etc. These are vector space. Then let's take a subset of this vector space. Let's say we take v1 to v3. So there is a subset of this space which is v1, v2, v3. We say this is a subspace of v. This is a subspace of v. Why? Because it follows three things. 0 is a part of S. If you add here 0 or if you subtract 0, answer will be the same. You will get the same numbers in the, you will get the same number of vectors here because 0 doesn't have any value. So 0 belongs to this S subset. S is closed under vector addition, that is x and y. Let's say this is x, v1, and this is y, v2. If you add this, you'll get something v3. So that should also lie under the same space. That is the what we saw in the first time, that if you multiply the two vectors, you'll also get the same space where it lies under the same set, same vector. And third is it is also closed under the scalar multiplication. That is, if you multiply any of it vector, let's x. So this is, let's say this is x. So if you multiply v1 by, let's say 5, so 5 v1, then it should also lie under the S. S is what? This was space, subspace. So subspace is basically the subset of real numbers. Okay, this does not mean it is a subset of vectors or something. It is a subset of this real dimension, this like real vector space, which is of dimension n. So you should keep this in mind. This is like, it gets very confusing to differ between what is vector space and what is subspace and what is like space in itself. So yeah, there is a theorem for this. There's a theorem for this also. So it just says that let S be the subset of a real number with dimension n. Then S is a subspace of R raised to power n, R of dimension n, if and only if the following conditions hold, which is S is non-empty. Non-empty means it has something. 0 is something, so it follows for any a comma b belonging to real number. These are just the scalar values, and any uv, these are vectors you can see by arrow, which belongs to S, which is same set which I showed you earlier. If you do the scalar multiplication AU plus BV, that also belongs to the S. So this is just the addition of this. So we say this is the theorem for this. Okay, right? So don't worry about it that much. Then we find the examples of subspace for this. Let V over the field R with the vector space. Then S comma S belongs to, S has the 0 and S belongs to V are subspaces of V. These are called trivial subspace of V because if the V is same as S, then this is V, right? This is V. Then you can say 0 also lies, 0 also is a part of this vector or this this set. If 0 also is set, it is non-empty and the first condition is hold. If S equals to V, so these are called trivial subspaces of V. Trivial because it is there, it is the same. Okay. So that is the first example. Then second example is set of all 3 cross 3 skew matrix or symmetric matrix is a subspace of vector space V, which is defined as V equals to M3 cross 3. 3 cross 3 is a matrix. M is a 3 cross 3 matrices with real entries. So we say as for ML, we get real entries only. So we are saying that. Now, what is skew schematic and symmetric matrix? So I'll tell you this with a brief example. You'll understand it very quickly. So we have any matrix. Let's say A is a 3 by 3 matrix, 3 cross 3. So as you all know, there will be some elements here. Let there be any real number element. Okay, this belongs to the this belongs to the real space, right? This belongs to the real space. But I'm saying if this is a matrix, there is also a transpose, right? So if it is symmetric, then a transpose will be equal to a. Meaning what? Meaning, let's get one thing for 1 minus 1, 1, then 1, 2, 0, then -1, 0, and 5. If you find the transpose of it, let's find the transpose of this. What is the transpose of this? The transpose of this is first 1, 1, -1, 1, 1, -1. This was column. I'm doing it by row. This is column -1. Okay, so I guess 1, 1. This is not okay. I did something. This is not. Sorry, guys. This is not this. Yeah. So 1, 1, -1. I put here. Then 1, 2, 0. 1, 2, 0. And then -1, 0, 5. -1, 0, 5. Isn't it same? Isn't this same? So that is what we call by symmetric matrix when the elements are same in the transpose way, in the diagonally. So if you mirror this, you'll get the same thing. So this is like the A transpose equals to A. This is symmetric. What is skew symmetric? Uh, this is symmetric. What is skew symmetric? So skew symmetric is skew means what? Almost symmetric, but it's not symmetric. Okay. So in this A transpose equals to negative of A. So this is like you can do it by yourself. I'm just giving it to you. If you have 0, -1, no, sorry. If you have 0, let's say 0, 1, and then -2. Yeah, 0, 1, -2. Then you have -1, 0, and 3. Then there's also 0 here. And then two numbers, let's say 2 and -3. Now find the A transpose of this and compare it with A and A minus. You will get your answer. That is what is skew symmetric. Okay. So understand this relations. You will know everything. This is symmetric. This is skew symmetric. All this second statement. I just told you this definition because you should get the second statement, which is set of all 3x3 skew matrix and symmetric matrix is a subset of space V. Why is it subspace of B? Because 0 is the element of A and S is no. This is like this is the first property. 0 is the element of that. If you do the vector addition, it also belongs to the same set S, and S will be closed under scalar. If you also scale this, you will get the same answer. That's why. So you can also prove that, but that is like, if you want to do it, you can do it. I'll not show it to you because it's not necessary right now to know. You can do it though, but for maximum utilization of our resources, we'll go away. We'll not think about that. But now I hope you understand what is vector space, what is subspace, and what is the what are the properties that holds it together and what does it run on. Okay, because we have gone very far. Okay, so this was our example of subspaces, right? Now let's see the result on this subspaces. So we are saying the intersection of any non-empty collection of subspaces of Rn is a subspace of Rn, and then union of two subspaces of Rn is a subspace of Rn if and only if one of them is contained in it. What are they saying? It sounds too jargonish or something, but it's very, very easy if you understand it geographically. Okay. Let us say there are two sets. One is set 1, one is set 2. If they intersect at some point, this is A intersection B. If this was governed by some set of operation and this was governed by some set of operation, doesn't this also governed by the same set of operations? So that's what this is saying. The intersection of any non-empty collection, because this is not empty, there is something, right? Of subspaces of Rn R with dimension n is a subspace of Rn. So this is the same. It is a subspace of R real numbers. Okay. So if there are real numbers here, and if there are real numbers here, there should also be a real number here. Okay. So that is what it's saying. And what is the union? For union, we'll say there is a union, and if the union of two subspaces of Rn is a subspace of Rn if and only one of them is contained in them. What does it say? Let's say there is this sector A, there is set A, there is set B. The union is what? Empty. If union is empty, tell me, is there anything here that correlates, or if they, can you find a subspace for this? No, because both are different, both are very different. But if A is big and B is lie under this, then the same operations performed here will also be performed here, and the both will be in the same subspace. Okay, so if two subspaces of R, A and B, is a subspace of R is for N also, because union is also the subspace, because one is contained in the other. So you can get this by the diagram itself. Okay, so this is also very uh, geometrically you can see it's very easy. Also, you can find the subspace for the polynomials also. So if the polynomial of one dimension, then there is uh, like if there are polynomials up to three, then how do you find it geometrically? So first is line, first is point, then there it is line, then there is a point at something point, and then there is a 3D plane. All of this lie under the same subspace. Okay, it is just for like, just for you to know, nothing to worry about. If even if you don't understand it, it's fine. um, yeah, so we saw the results on subspace. Now let's see the linear span. So what is linear span basically? So let let V of X be the vector space. So V of F is a vector space, and S is a non-empty subset of this specific V. Okay, then the set L of S, which is the linear span of the set of S, is C1 V1 C2 V2 Cn Vn. So remember in the first lecture we had something of a linear combination, where we had we did the linear combination of the row vector spaces, and we put them in the order. There was alpha v1 plus alpha v2 plus alpha v3, that alpha v1 plus alpha v, you remember this, right? This is the same as this. So this is the linearification, linear span of the space. Okay, so this is C1 V1, C2 V2, Cn V1, Ci belonging to real number, and I is one between the 1 and. So this is you can understand this by example, right? You don't need to study it. Then let's say there's another set. One, let's understand this by example also. What is linear span? So there is 1 0, there is 0 1, and then there is, let's say, anything like C1 and C2 are the C1 C2 are the C1 C2 are the two constants. Okay, whatever, like whatever real number you want to put, 5 3 2. Okay, if you have the linear span of this, I'm talking about this, right? This, I'm talking about this. So what will it be? C1 what, 1 comma 0, then there will be what, plus C2 0 comma 1. Then how do you add it? How do you add it? Do you remember? You should just do what? C1 into 1 plus C2 into 0 0. So C1, then C1 into 0 0 plus C2 into 1 1. So C2. C1, C2 into 1 into C2. So C2. So this is what the answer is. This also belongs to what? Real number. Why? Because this belongs to real. Ci belongs to R. Okay, so same can be said for the R3 also. You don't have to do it, like you can also do it by hand, by yourself. Okay, so you can say the same about the R3, which is like dimension 3. If you took these three values, just take this three value 1 0 0 1 0 0 0 1, and when you multiply it by C1 C2 C3, you will get that C1 comma C2 comma C3, which will also belong to R. So it is same. Then third example is if S is an empty set, then L of S equals to 0 vector. So that is also true. Then that is also can be like simplified, because 0 is what, L is equals to 0 vector. You can put this in the set in itself, it won't matter. So that is also an example, like same split. Then let S equals to 1 comma 1 comma 1 2 1 3. So this if is a subset of R3. R3 is like three dimensions. So we have three dimension. Okay, this is 1 1 1, this is 2 1 3. This belongs to subset of R3. So it is third dimension, and F equals to R. Then the linear span of this is just do C1 1 1 1, C2 2 1 3, and this C1 C2 belongs to real number, right? If you do this, then you will get C1, then 2 C2, then you will get C1, then C2, and then third you will get C1 plus C3 C2. Okay, and then you'll find that this all is just a real number x1, x1, x2, x3. Okay, so this is in the just of the format 2x1 minus x2 equals to x3 format. If you do this here, like it just uh 2x1, so this is what, x2. Okay, so you'll do 2c1 plus 2c2, then you will do what, minus x2. Okay, so this was 2x1. Okay, sorry. Yeah, so it is first 2c1. So 2c1 is what, c1 plus 2c2, it is 2c1 plus 4c2. Then you will do 2x1 minus x2. Minus x2 is what, c1 minus c2. c1 minus c2. This is c2. Okay, right? This is like, if you do this, what is the answer? C1 is only remaining one, and C2 is 3C2. If you understand this, X3 is what? C1 plus 3C2. So answer is same. Okay, so like this is like find, these are the like x1, x2, x3, and this is like you finding the relation between them. If you find the relation between them and they belongs to the real number, then x1, x2, x3 belongs to the R, that is your third dimension. Okay, so this is like easily proof. So you can get like n number of examples from this, and it is very easy to do. You just have to find some correlation and then build upon that sense or intuition, and it is easily doable. Then some important subsets. So let's say for this, we'll say this is like just for vectors. What if you could just combine lot of vectors? Then what you will get? You'll get matrices, right? So matrices is also a subspace of that S. So here Aij belongs to R. Then the row space of A is given by linear span A1, A12, and so this is like up till AMN and is a subspace of R dimension n of field R. So how do I, why do I say this? Because this is like the row space. Row space is like what you go from here to here. So it is n R of the dimension n and belonging to real of the field R, because all of this is R and this is like only one. So this is only, we are talking about linear space of matrix. Okay, if you go by column, let's say we go by column, then what will be the answer? We are going by row, so we get 1, 1, 1, 1, 2, 1, 3, 1n. So up till n. If we go by column, then we'll go by 1, 2, 3, 4, 5, and m. So we'll get this, then this, then this. What will be the, what will it, this be the subspace of then? This will be the subspace of R raised to power m dimension over the field R. So this is R vector of m. This is one vector. This is two vector. So this is one vector. This is two vector, and of over the field R. So this will be the same. Just we do this. We'll do this for a column, and we'll get the same answer. So let's see if we get the same answer. Let's move forward, because this is the row space. There is also column space. Column space is what, C R raised to power m R. So yeah, that is how things goes. Also, the set NA equals to X belonging to R of n dimension, AX equals to 0, is said to be null space of A. So what is exactly the null space of A? If A is any matrix, then a null space is said to be that vector which makes the multiplication 0. So AX equals to something 0. So if multiplying A vector by this vector, if multiplying A matrix by this matrix here makes it 0 vector, then that is said to be a null space. So here it is given exactly that the set NA equals to X belonging to Rn, AX equals to 0 is said to be a null space of A. This is also like just examples of the vector space. Then the set Ra equals to B belonging to Rn, AX equals to B. So if there is AX equals to some B for X belonging to some real number, it is said to be the range of A. So generally what happens that this is same as the column space. So whatever the column space of matrix you have, that is the range of matrix you have. So A is nothing but matrix. So column space is equals to the range of the matrix. Okay, that is its range. Then yeah, so this is like the another example. Then we have finished this vector space thing. Now what's remaining is basis and dimension, which will complete maybe in the next lecture. Then slowly we'll uh, do away with the linear algebra. And then let's see what we'll get next. But yeah, so this is the part. Okay. Hope you understand it. Maybe you learned something. Maybe you didn't. Let's see. If you learned something, then that is very nice. Okay. Bye.